All right, guys, so this is our first Flip the Classroom lesson of the second semester. In this lesson, we will be talking about simplifying trig expressions and proving equivalence statements for trig expressions. So what do we mean when we talk about trig expressions? Well, with trig expressions, basically we're looking at expressions that are multiplying, dividing, adding or subtracting trig functions. We've got an example of a trig expression right here. Here we're only multiplying and dividing, but we could be adding and subtracting as well. In general, we want to take note of a difference in notation with regards to powers. In our numerator right here, we've got sine squared x, and really what that's saying is the ratio of sine of x squared, right? Whenever we are raising a trig function to a power, we always apply that power directly to the trig function itself, right? And this avoids any confusion with potentially having the rotation inside the trig function being raised to that power. So right here, in general, when we're simplifying trig functions, we're going to be saying that we are evaluating these trig functions for a unique angle. In this case, that angle is x. And basically what this means is that we're going to be getting numbers, right, for these ratios that we'll be able to cancel out. In other words, right here, the sine x we're squaring in the numerator, right, is going to be the same number as the sine x we're seeing right here in the denominator of our expression, right? Now, because these ratios are representing unique numbers that we'll be able to cancel out, we're really going to be able to simplify these expressions in the exact same way we would simplify an algebraic expression involving just variables. Here we have an algebraic expression involving just variables that is algebraically identical to our trig expression, where sine is represented by y and cosine is represented by x, right? If I were looking at this algebraic expression involving just variables, I might start by simplifying the denominator. Right here I can see I am multiplying x times y over x squared. Right here I'm going to be able to cancel out the x I'm multiplying with one of the two x's I'm multiplying in the denominator of my denominator, and that will give me y squared over y divided by x. And now right here I'm dividing by a fraction, which is the same thing as multiplying by the reciprocal. So right here I can say I've got y squared times x over y. And similarly, again, we can cancel one of the y's we're multiplying in the numerator by the y we're dividing here, and we will get this expression as equal to y times x. Now, basically, when we simplify our trig expression over here, we're going to see all of the same algebraic moves. Right here, I'm multiplying cosine, and I've got cosine squared in the denominator, so I'm going to be able to cancel out one of the cosines in the denominator of my denominator. Then I've got sine squared x over sine x cosine x. And now right here, I can say that I've got sine squared x times the reciprocal, cosine x over sine x. And now we can cancel out sine x's, and we're going to be able to say that this statement is equivalent to sine x times cosine x. Now right here we can see that this expression would be a lot easier to evaluate for an angle x than our original expression right here, right? So we can see the value of simplifying trig expressions pretty much right away. Now, in general, we're not always going to be evaluating or simplifying trig expressions that are so readily easy to simplify. If we were looking at something like secant theta over cosecant theta times tan theta, we would have to say that we couldn't immediately cancel out any trig functions in the way that we did with our first expression right here. But what we're going to be able to do is use what we call trig identities to make substitutions where we'll be able to represent an expression like this with some of the same trig functions, and then we'll be able to cancel out just like we did right here. So let's go ahead and start defining those identities. So what is a trig identity? Well, a trig identity is basically a way we can represent one trig function with other trig functions, or just another trig function in general. All right, so right here, we'll start by defining our basic identities, which are made up by our reciprocal identities and our quotient identities. In general, we can start defining our reciprocal identities right away just by looking at trig functions as we define them on the unit circle. So right here, we can say that cosecant of an angle theta is going to be 1 over y. Well, we know that on the unit circle, sine of theta equals y. So right here we can say cosecant is actually 1 over sine theta, or could be defined as 1 over sine theta. If we solved for sine with this expression right here, we would get 1 over cosecant theta, right? Similarly, right here we can see that secant on the unit circle for an angle theta is 1 over x. We know that cosine is x, so we'd be able to define secant as 1 over cosine of theta. And right here, if we were to solve for cosine, we would get cosine as 1 over secant. Really what we're seeing here is that we can define trig functions as 1 over their reciprocal, and we can extend this to tan and cotan. Tan is going to be 1 over cotan of theta, and right here, cotan is 1 over tan of theta. And in general, we've already done this when we've evaluated trig functions in the calculator. Right here, if we want to evaluate cosecant of an angle, we would generally type in 1 over sine of that angle, and we'd be able to see that number on the calculator. So we've already seen this before. We're just sort of defining it in terms of these reciprocal identities that we're going to be able to use in our simplification of trig expressions. So right here, the quotient identities are actually pretty easy to come by. We know that tan is y over x, right? So right here, that's going to mean that we can say that tan of theta is equal to sine of theta over cosine of theta. And cotan we know is x over y. And right here, we're going to be able to say then that cotan of theta would be equal to cosine of theta over sine of theta. And one thing we might want to take note of right away is that every trig function can be defined by sine and cosine in some way. We've got the quotient identities for tan and cotan. We've got cosecant as 1 over sine, and secant as 1 over cosine. And of course, sine and cosine are themselves sine and cosine. So in general, one thing that we can take note of is just with our basic trig identities, we could define every trig function with sine and cosine in some way. The Pythagorean identities come from us looking at reference triangles on the unit circle. So right here, let's say I've got a reference triangle on the unit circle that comes from some rotation theta. Well, right here, I know that the opposite side is going to be y. I know the adjacent side is going to be some x, right? For some ordered pair, we have as x, y on the perimeter of the unit circle. And I can say that the hypotenuse of this reference triangle is going to be r, which we know to be of length 1, right? So let's take this reference triangle and bring it down and take a look at it. Now, if I were to apply the Pythagorean theorem, I could say here that for my reference triangle, which is a right triangle, I have x squared plus y squared equals r squared. Well, right here we know on the unit circle that the x values are cosine of theta. So right here we could substitute in for x cosine and get cosine squared theta, and we know that the y values are sine of theta. So right here we could substitute in sine of theta and get sine squared theta. Similarly, right here we know, since this is a reference triangle within our unit circle, that r is 1. So right here we've got cosine squared theta plus sine squared theta equals 1, and that's our first Pythagorean identity. Right here we get the other two Pythagorean identities by dividing by sine and cosine. Right here, if I take this expression and divide both sides by cosine squared rather, if I divide both sides by cosine squared, I can distribute the division of cosine squared to both terms on the left side and get cosine squared theta over cosine squared theta, and sine squared theta over cosine squared theta. And right here, cosine squared over cosine squared is going to be 1. We have sine squared over cosine squared, which will give us tan squared theta, and 1 over cosine squared theta, which with our basic identities we can identify as secant squared theta. So that's our second Pythagorean identity. Now right here, if we go through and divide everything by sine squared theta, in the same way we divided everything by cosine squared theta, we can distribute that division of sine squared theta to both of the terms on the left again. And right here, we'll be able to see cosine squared theta over sine squared theta as cotan. Sine squared theta over sine squared theta is 1, and 1 over sine squared theta is cosecant squared theta. And there is our third Pythagorean identity. So there are the Pythagorean identities and the basic identities. Now right here, we can talk about even and odd identities. And basically, this comes from the fact that every trig function is either even or odd, right? And we can see that from the graphs of our trig functions. Right here, if we were symmetric with respect to the origin, basically being reflected diagonally across the origin, we would say we are odd. And if we are symmetric with respect to the y-axis, we would say we are even. So right here, immediately, we can say that sine is odd, cosecant is odd, tan is odd, and cotan is also odd. Since all of these trig functions are odd, we know that by the definition of odd functions, which tells us that if a function is odd, when we plug in a negative x, it's the same as making the function negative. That right here, when we plug in a negative rotation, it's the same as making that trig function negative, right? So immediately we can say that sine of negative x is equal to negative sine of x, and that follows for all the other odd trig functions. Right here, we can see that cosine and secant are even trig functions. They're both symmetric with respect to the y-axis. So right here, by the definition of an even function, we know that when we plug in a negative x into an even function, so f of negative x, we get the function back. It's the same as plugging in a positive x. So right here, we know that cosine of negative x equals cosine of x, and secant of negative x would equal secant of x. Right? So that's basically a way for us to deal with negative rotations inside our trig functions. So moving on, we can move on to our co-function identities. Now right here, we've got a reference triangle with an angle of perspective A. So there's the angle perspective A in our reference triangle. But what if we were to change the angle perspective from our angle A to our angle B? When we look at our triangle from angle A, we can say that the y value is the opposite, or the y length is the opposite length, and that the x is the adjacent. And we know r is always going to be the hypotenuse because it's opposite the right angle. But what if we were to take B as our angle perspective? Well, then the y would change from opposite to adjacent, and the x would change from adjacent to opposite. So right here, we can say that sine of A equals y over r, but cosine of B also equals y over r. Similarly, right here, if we look at cosine of A, that's x over r, but right here, that's also sine of B. And if we go down, we can sort of see this relationship with all of our co-trig functions. So right here, tan of A is y over x. But if I switch these two guys, that would be basically looking at the reference triangle from that angle B. We switch opposite and adjacent, and that gives us cotan of B. Right? So switching the angle perspective is really switching our definitions of opposite and adjacent. And what we're getting is the cotrig functions from that other angle perspective. So secant of A is cosecant of B. And right here we can say cotan of A is x over y, but right here tan of B would also be x over y, and cosecant of A is r over y, but right here we could say that secant of B would also be r over y. So the relationship we're seeing with trig functions and their cotrig functions is that the cotrig functions are basically the same ratios from that other angle of perspective, right? So if we can define that other angle of perspective, really we've got an identity here. we can say that we know that since this is a right triangle, that C is 90 degrees, right? And that means since a triangle has 180 degrees, that A plus B must also equal 90 degrees. Now, if we define B as that other angle, we could say that B would be 90 degrees minus A, right? So the other angle is always going to be 90 degrees, or a right angle minus A. Now, in general, we're not going to be defining our angles in degrees here. We're going to be defining them in radians. So right here, for an angle theta of perspective, the other angle, and I'm going to use that little symbol for the other angle, is always going to be equal to pi over 2, which is a right angle in radians, that's equal to 90 degrees, minus theta, right? And right here we've got these identities laid out for us. So right here, if we look at these identities now, see if I can pull that down, we've got sine of theta as equal to cosine of the other angle. And that's how we want to think about our pi over 2 minus theta, right? So cosine of pi over 2 minus theta is the other angle in that reference triangle. Tan of theta is equal to cotan of the other acute angle, or the other possible angle of perspective. Secant of theta is cosecant of the other angle, and we see the same thing for the cotrig function. So cosine of theta is equal to sine of that other angle. And those are this is the co-function identities here. All right, guys. So in this video, we are going to simplify trig expressions for a unique angle theta or x. Our goal here is to reduce down the expression to the least possible number of multiplied trig functions, not necessarily sine and cosine in the numerator. We've got a couple strategies we're going to look at here. The first is if the expression is in terms of multiplication and division, we're going to try to convert all of our trig functions to terms of sine and cosine. And there we should be able to see things cancel out, which will, of course, reduce down our expression. Our second strategy is if we see addition or subtraction in our expression, we're going to try to use a Pythagorean identity to substitute one term for two terms, and that's going to hopefully get us back to a place where we've got everything in terms of multiplication and division. We can change everything to sine and cosine and cancel things out. All right, so right here we're going to look at A first. And then we're going to let you guys try B. So right here with A, we've got secant theta over cosecant theta tan theta. Now right here, everything is in terms of multiplication and division. So immediately, I can change everything to sine and cosine, right? So for secant theta, I'm going to have 1 over cosine theta. And for cosecant theta, I'm going to have 1 over sine theta. And then my tan is going to be sine theta over cosine theta. Now immediately in the denominator, we're going to be able to cancel out our sines here. And that is going to give us 1 over cosine theta in the numerator over 1 over cosine theta in the denominator. Now clearly right here, this is going to be equal to 1. But in terms of just sort of practicing algebraic moves that we're going to use over and over again, I'm going to say that this 1 over cosine theta in the denominator can be written as a multiplication of the reciprocal. So I'm going to have 1 over cosine theta times cosine theta over 1. And of course here my cosine thetas cancel, and I get my entire expression to simplify down to 1. Now right here, basically what we're saying is that all of the thetas in our expression are going to be the same angle, right? And whenever we're plugging in one angle theta into this expression, the ratios of secant, cosecant, and tan are always going to reduce down to 1. So that's a nice simplification for us. In general, right here, we're only able to make these conversions and cancel things out when all these angles are the same, right? So in our next example B, we've got pi over 2 minus theta, and then a negative theta inside the 3 trig functions that we're multiplying. We'll have 4 with cosine squared. But what we're going to want to do first before we start thinking about simplifying this down is change each of these trig functions so that they've all got the same angle inside, and that's going to be the angle theta. So right here, I'm going to pause the video here and let you guys try B on your own, and we'll come back and look at this in a second. All right, guys. So right off the bat, we want to use co-trig function identity right here to substitute secant of theta for our cosecant of pi over 2 minus theta. And we want to use the fact that tan is odd to let us write our tan of negative theta as negative tan of theta. Now we've got everything in terms of trig functions evaluating that same angle theta, and everything's being multiplied here, so we can convert to terms of sine and cosine and let things cancel out for us. So right here, our secant is going to be 1 over cosine. We've got cosine squared, which we're just going to let be cosine squared. And we've got our tan, negative tan of theta, which we can convert to negative sine theta over cosine theta. And then right here, what we're going to see is our cosines cancel out. So we've got our cosine in the denominator of our first multiple, canceling with one of the two cosines we're multiplying in the numerator of that second multiple. And then right here, the cosine in the denominator of the last multiple, canceling with the second cosine we're multiplying in that second multiple. And we reduce down to just negative sine of theta. Okay, so in C, D, and E, we are seeing addition and subtraction in our expressions. And so right here, what we're going to want to do is, of course, use a Pythagorean identity to substitute one term for two terms, so we're back to that case where everything's in terms of multiplication and division. So right here, I'm going to do C, and then I'm going to let you guys try D and E on your own. Right here with C, immediately we've got secant squared theta minus 1 over cotan theta. Now, right here, that secant squared is a good sign because we know our trig functions need to be squared to use the Pythagorean identities. Right here, the trig function, or the Pythagorean identity rather, involving secant is 1 plus tan squared theta equals secant squared theta. So I'm immediately going to the Pythagorean identity that involves secant. And right here what I can see is if I subtract 1 on both sides, I've got that expression in the numerator. So right here I can say that tan squared theta equals secant squared theta minus 1. And that means that I can substitute tan squared theta in for my secant squared theta minus 1. And right here I'm going to have tan squared theta over cotan theta. Now at this point we could change everything to terms of sine and cosine, but we know that tan and cotan are reciprocal trig function. So what I'm going to do is, instead of changing everything to sine and cosine, I'm going to take a little bit of a shortcut, and I'm going to say that I know I can write that cotan in the denominator as 1 over tan theta, and then right here I'm dividing by 1 over tan, which is the same as multiplying by the reciprocal. So now I've got my tan squared theta times tan theta, and that's going to give me tan cubed theta as the simplified expression. Okay, so right here, that's C. With D and E, you're going to try to use some of the same principles here. D is pretty straightforward, but E has got a little bit of a twist to it. Right here, what you'll want to think is you're seeing that tan squared theta in an addition, so you're going to be able to sort of, you want to try to think about using the Pythagorean identity involving tan, and right here you want to think, how can I get that tan by itself so that I've got just something plus tan squared theta. So right here we'll pause the video and let you guys try D and E on your own, and we'll come back and look at these in a second. All right, guys, so let's take a look at D and E. Right here, initially with D, we can see that we've got just squared trig functions, so we're right for using a Pythagorean identity. In the denominator, we have some subtractions that we're seeing here. So we're going to group our trig functions so that they give us a Pythagorean identity. Secant and tan are in a Pythagorean identity together. So right here, we're going to rewrite our expression so that secant and tan are next to each other in the denominator. Right? Got secant squared theta minus tan squared theta. And right here, we can say that with the Pythagorean identity, we have 1 plus tan squared theta equals secant squared theta. So right here, if we subtract tan squared theta and subtract tan squared theta from both sides, we're going to get secant squared theta minus tan squared theta equals 1. So right here we can substitute 1 for our secant squared theta minus tan squared theta. Now right here we've got 1 minus sine squared theta. We want to look to try to substitute one term for two terms right there with a Pythagorean identity. So going to the Pythagorean identity involving sine, we've got cosine squared theta plus sine squared theta equals 1. And right here, if we subtract sine squared theta from both sides, we've got cosine squared theta equals 1 minus sine squared theta. So right here, we can substitute in cosine for our 1 minus sine squared theta there. And now in my next step, basically I did two things at once. I changed cotan squared theta to cosine squared theta over sine squared theta, and I took the division of cosine squared theta and made it a multiplication of 1 over cosine squared theta. And right here what we can see is that those cosine squared thetas are going to cancel out, and we've got 1 over sine squared theta, which equals cosecant squared theta. And that's our reduced simplified expression. All right, so with E, right here we can see that we've got a tan squared theta times secant squared theta. And we can also see that secant of theta is a multiple of both of our terms here. So right here that means that we can factor it out such that we have secant of theta times 1 plus tan squared theta. And right here, 1 plus tan squared theta is, of course, immediately a Pythagorean identity. And so right here we can substitute in secant squared theta for our 1 plus tan squared theta, and then right here we've got secant theta rather times secant squared theta, giving us secant cubed theta as the simplified expression. All right, guys. So what we're going to do now is move on and look at some proofs. Right here, proving trigonomic equivalence statements. Basically, these are going to be, we're really doing all the same steps we did with simplification, but now we're trying to show that two expressions are equal. And when these proofs, basically what we're going to do is we're going to be using a step-by-step process to show how one side of the equation is obtained from the other. So that basically means we're going to take one side of our equation and work with that one side of the equation to show that it equals the other side of the equation. So this isn't something where we're subtracting things from both sides or going from one side to the other with algebra. We're basically just taking one side of our equivalence statement and manipulating that to show that it equals the other side. Right, so we're going to look at A together, and then I'm going to let you guys try B and C on your own. So right here, I've got cosecant theta minus sine theta equals cosine theta times cotan theta. And in general, we want to start out with the trickier side of the equation. So right here, I would consider this side to be more simplified. So I'm going to actually start with the left side of my equation here. And immediately we can say that we've got a subtraction. So we're going to want to use a Pythagorean identity at some point. But neither of our trig functions are squared, and they're not related in a Pythagorean identity. So what's a good strategy here is, if we're not seeing any way to sort of bring these guys together with a Pythagorean identity immediately, is to change everything on the left side of the equation to terms of sine and cosine, and see if we can somehow bring these two terms together in some other way. So we've got our cosecant of theta as 1 over sine theta, and then minus sine theta. Now right here, what we can say is that the right side of the equation that we're trying to get to is basically one term, right? It's two things being multiplied as one term. So basically right here, what I want to do at this point is bring my two terms together and try to make them one term, and I can make them one fraction by getting common denominators. So right here I can multiply my sine of theta by sine theta over sine theta. And now I've got common denominators, right? I've got 1 over sine theta, and then minus sine squared theta over sine theta. And now right here I can bring these two guys, these two terms together and make them one fraction term, 1 minus sine squared theta over sine theta. Now, just in doing that, in bringing my two terms together to be one term, I've already got some nice things happening. We've already got sine squared now, and then we're subtracting sine squared away from 1. So we know that that's going to be something where we can substitute using a Pythagorean identity. And right here what we're saying, of course, is that cosine squared theta plus sine squared theta equals 1. And we already know from the previous page that right here when we subtract sine squared theta from both sides, we've got cosine squared theta and then equals 1 minus sine squared theta. So right here, we can make that substitution and get right here our cosine squared theta for our 1 minus sine squared theta over sine theta, not sine squared. Now, at this point, when we got our expression sort of condensed down to multiplication and division, what we want to do is take a look back at our target expression, right? So there's going to be a place where we've taken the more complicated side and simplified it as much as we can. And then what we want to do is see how we can manipulate that simplified expression to get to our target expression. Well, immediately right here in my target expression, I'm multiplying cosine. I've got cosine squared in the numerator here. So right here, I can say if I factor out a cosine for my numerator, I'm going to have that multiplication of cosine times cosine theta over sine theta. And right here, what we can say then is with our cosine theta over sine theta, we've got cosine theta times, and cosine theta over sine theta is cotan theta. Now, right here, in general, we're always going to be, when we take the more complicated side of the equivalence statement, really what we're doing is looking to simplify to a place where we can then manipulate that simplified expression to get our target expression, which is what we've got right here. That might not always seem obvious, but I think it gets clearer and clearer the more you try these. So right here, why don't you guys go ahead and give B a shot, and you can give C a shot too. It's a little challenging. What I would say is with C, you want to start to think about C in the same way that we looked at D on that last page. You're going to have to do one sort of substitution first, but then you're going to be pretty close to it if you can think about factoring out. And again, I would start with the more complicated side being the side where you're actually adding and subtracting trig functions, so that reducing is getting you closer to that target expression. All right, guys. So why don't you guys pause the video and give this one a shot? All right, guys. So let's take a look at these two. With B, we take the more complicated side, the left side here. And immediately we are having trouble condensing things with a Pythagorean identity. So changing everything to sine and cosine, we get our secant x as 1 over cosine and our tan squared x as sine squared x over cosine squared x. Now immediately right here, by multiplying by the reciprocal with this guy, we can say that we're going to have 1 over cosine squared x minus sine squared x over cosine squared x. Now we've got common denominator, so right here we can say we've got 1 minus sine squared x over cosine squared x. And right here we know 1 minus sine squared x is going to be cosine squared x with the Pythagorean identity that we manipulate a little bit. And cosine squared x over cosine squared x, it's going to give us 1. Right, with C, we said that we wanted to use some factoring. Again, immediately, if we take the left side of the equation, it's the more complicated side. Right here, we can't, even though our trig functions are squared, cotan and cosine are not related with the Pythagorean identity, so we're kind of stuck there. But what we can do is change everything again to terms of sine and cosine. So our cotan squared theta would give us cosine squared theta over sine squared theta. Now right here what we can see is that cosine squared is a factor of both terms, and we can factor it out of both terms, right? Our target expression helps us a little bit here because our target expression has cosine squared theta in it. So right here we can say, all right, well, if I factor out that cosine squared theta, I'm multiplying by cosine squared, and whatever's left should be equal to cotan squared theta. So right here, what's left is our 1 over sine squared theta minus 1. Right here we can say 1 over sine squared theta is cosecant squared theta, and then minus 1 we can again substitute with the Pythagorean identity cotan squared theta, and there's our target expression. All right, guys, we're going to do one more new thing, and then we are going to call this. We want to look at one more sort of advanced strategy with simplifying trig expressions and improving these equivalent statements. We'll look at that in the next video. We'll stop this video here, and we'll do one more quick video, and then we'll call it.